Greetings of the day, everybody. My name is Dr. Gourav Kumar Suman from the Department of ECE, Madanapalle Institute of Technology and Science, Madanapalle. And I'm here with a series of lectures on control systems engineering. I'm really thankful with an heartfelt appreciation for the management of Madanapalle Institute of Technology and Science and the MITS radio station for these series. So let's begin here. Now, today we are going to observe or go through the first set of introductory lectures on control systems engineering. The first module today will discuss on introduction to systems and control. Now, in the perspective of engineering, we engineers tend to make the progressing lives simple. We do this by observing each and everything around us and how we can simplify it. It is the foremost task of an engineer to make a complex system look easy. This particular subject, control system engineering, it forms quite a multidisciplinary uh, subject, we would say, which covers various aspects of engineering all together in a single envelope. Now, say for instance, a man who is driving a vehicle, he doesn't have an idea about the system which actually is inside. However, the engineers have strived, have worked hard to bring that system in such a way that it is user friendly to the drivers, so on and so forth. We can observe all the real life systems around us. Now, before using the word systems with such a simplicity, we'd like to explain what exactly a system is. So, by the course of this particular session, we'll be covering up the overview of the system. Let's have a look onto it. We'll discuss what is a system. We'll observe various classifications of the system in terms of linearity, in terms of dynamism, in terms of time variant features, whether it is causal, non-causal. We'll see what a control system is as a whole. We'll check what's a disturbance in a system, some feedback, and some examples. Now, to begin with, a system can be considered as an arrangement of any physical, biological, or abstract components which are connected in such a manner that it performs or serves a particular task, working together as a single unit. In the most basic form, a system can be defined as uh, a combination of some sort of processes which will respond to an excitation, and the excitation can be of any form. It can be physical, it can be an abstract excitation, or it can be biological for that matter. Now, when it comes to engineering, it's really tough for the students to understand what brings in the abstract sense into systems or really in the studies of engineering. However, if we consider the most basic form of abstract system, like teaching learning mechanism, if we consider, here the input which is given to the system, I'm considering the students to be a system. The inputs which is given to the students, basically our system at this point, is quite abstract, as in the input which is delivered by the teacher, it cannot be quantified in terms of magnitude. However, based on whatever input is given, the students perform, and the output is checked in terms of examinations, or you would say in terms of assessments. That's what we do. This was an example for an abstract system. Now, if you consider a physical system, there are many things in and around us, and we, uh, because of their user friendliness, we keep on using these systems continually in a regular fashion. We do it daily. I'm doing here, you're doing there, we're doing it. But the concern is, we as an engineer have to realize the necessity of design of the dynamics of the system. Now, in the most basic form, a system can be defined as a combination of physical and abstract components which are connected in such a manner that they act like a unit and serves to perform a particular task. And this task can be user defined. Now just have a look onto this. This is one of the examples I'm going to put in front of you so that you observe what exactly a system would look like. Now, say for instance, here I have stated that in the most general sense, everything around us that we see, it can be considered as a control system. Let's have a look onto this. Here you would see on the screen, there is a mirror. It's a plain mirror, and there is a source and an observer. Basically, the eye-based sensing system, we would say, as we proceed further in the lecture series. However, we can consider the source and the observer. By basic laws of reflection, we know the angle of incidence, that which is represented over here, it must be equal to the angle of reflection. This is a well-known law, known as law of reflection. Right. Now, this can be defined as a system. Now, let's see how we can control it, how an engineer uses his technical abilities, or rather say logical thinking, and makes it look like a control system. Let's see how we can control here. Just have a look onto this. The same setup. However, now we have a wall on which the mirror is suspended, or rather we say it is attached to the wall in such a manner that there is a screw which is connected to the mirror. Now, by changing or tightening or loosening the screw, we can change this angle theta. And by that change, we can control where exactly the reflected ray is being deposited. Here still, the law of reflection, that is angle of incidence and the angle of reflection, it would be equal. But by controlling the position of this particular screw, we can change the angle theta, and that can define where exactly the reflected light is being deposited. This can be a screen for that matter. I've just kept an eye for an illustration. However, this can be a screen, no problem. Now with this, this is one of the most basic system which I explained just now. Now we can have a look onto our daily life things. I mean, the mirror and the reflection is quite what we have done in young ages. Now we can see certain examples in form of, say, electric motor. The example that we saw just now was that of a plain mirror, which we have played early on when we were young. Now let's have a look onto an electric motor. Now, we are all aware of an electric motor. It basically takes electrical energy as the input and delivers us in form of an energy in the form of mechanical, rather. And suppose I'll just show you. Here, the input over here is an electrical input, and there we can see a good old motor and a mechanical output. Let's have a look onto it. Yeah, that's it. Now, the moment we supply electrical energy, the motor will be excited. Here I'm using the term excited because I'll be telling that electrical input is basically the reference or the excitation to the system of electric motor. And the output that you observe over here is the mechanical rotation. Now, this particular thing, electrical input, will be referred as the reference or the excitation, and the mechanical torque or the rotation would be called as output or the response of the system. There is another example for you, and that is an air conditioner. Now, an air conditioner too takes electrical energy as an excitation, and the response of air conditioner is basically the change in temperature of the surrounding. It is generally done in a closed room. Now, if for a closed room, we have certain ambient temperature, and we are using air conditioner to let the ambient temperature fall down to our comfortable level. And this can be done by varying the electrical input over there. Now, the moment we give electrical input, we'll observe changes in temperature with reference to the ambient. If we want to, suppose we can take an example of an electric heater as well, wherein in winter, the room temperature or the ambient temperature is quite low, and we are supposed to rise that up. and that we do with the help of an electric heater. There again, the excitation is electrical energy, and the response or the output is change in temperature. These are a couple of simple examples that we can observe for control systems. Now we move forward with classification of systems. Now there are numerous ways to classify a system. Now some of these are based on the features and applications of the system. Some of this classification, which we'll cover in this particular session, are as shown: linear, nonlinear, static, dynamic, time invariant, time variant, causal, and non-causal systems. Let's have a look onto them one by one. Suppose we see a linear and nonlinear system based on linearity, basically. Now, the output of a linear system, it varies linearly with the input. And basically, in other words, we can say it satisfies homogeneity and superposition. Whereas a nonlinear system, it doesn't vary linearly with respect to the input. And it doesn't satisfy homogeneity and superposition. Now, this I can show you with an illustration over here. Let's have a look. For example, if I consider a linear system, I could say, suppose I have a mechanism wherein I have a DC input. I have attached it to, say, a resistor based system. Let's assume the excitation be V and the value of resistance be R. Now you would know the moment the supply is on, or I have not placed a switch over here, so I'm considering it to be on. There would be a flow of current, maybe in this direction, clockwise direction, and I can say the relation I, it would it would be linear. Now, if I change the value of voltage, if I assume the value of voltage V to be a variable one, and I can trace down the plot, and the graph would appear to be linear, wherein with the change in input, I'll observe a linear variation in the output. Here I'm considering current as the output. Mind you, it depends on the designer what he chooses to be the excitation of the system and what he chooses to be response of the system. And based on these selection, he would be designing the system. Now here, for this particular example of a resistance excited by a voltage source, a DC voltage source, the response would be linear. Now, however, if I had to supply, say, the same DC source, and if I had to supply a diode-based system over here, now the current will not be linear. I would know that the current would depend on the saturation current in certain time constant, time once. It would be related, wherein this tau is the time constant. It would be related with in this manner. Now you can observe this. Say, for example, if I am about to explain you homogeneity, and if I take some alpha times the voltage which I supplied initially, if I take some alpha times that, now I know that the new current, let me mention it as I2, it would be alpha times V over R. And still the curve would be linear. However, the slope might change. That's quite agreeable. However, in this particular case, if I take alpha times V, the response over here, which looks like this, alpha times V over tau minus 1, this is never going to be equal to the actual to the response which we would have we would have expected in same as in the case of say a resistor unit. Similarly, if I consider superposition theorem, now say for instance, if I add another source over here with a magnitude v2, for instance, and here if I add another source here with a magnitude v2 for that matter, the response from this particular first system, the total response will be equal to the sum of both the individual responses. However, here the total response is never going to be it would never look like this. So I'll show you the equation straight away. So the total response will look like this: v1 plus v2 over the time constant minus 1, and it is never going to be equal to the sum of individual responses. And it is, let me write that out for you, v1 over tau minus 1 plus I naught times e to the power v2 over tau minus 1. It's never going to be equal. These sum will never look like what actually it should have given. Now, these two are the most basic examples of the linear and nonlinear systems. So, to repeat, I can tell you the response of a system, if you consider, is varying linearly with the excitation. We'll call it as a linear system. And if the response is not varying linearly, it has certain relation, maybe quadratic, it can be anything, it can be exponential. We'd call those systems as nonlinear systems. I hope it is clear. Let's move on to the next explanation, to the next division, static and dynamic systems. We have come across many static and dynamic systems in our real life. Let's have a look. Now, in a static system, the output of a system at a particular time, it depends only on the present input. And these are considered to be those systems which do not bear memory. Whereas a dynamic system, the output depends on the present input as well as the previous input. Here, the term memory is used in some logical sense. We'll consider a dynamic system to bear memory. Let's have a look onto that mathematically. Now, for the same case of a resistor being excited by a voltage source, suppose if I excite a resistor with a voltage source, I'll expect a current, like same as the previous case. I'll expect a current. What if, and this current is supposed to be V over R. There is no change in that. Or rather, I can say V is equal to IR over there. It's quite easier way to understand it. Now, say for example, if I suddenly replace this particular voltage source with a short circuit, If I do so, this will be the new equation, right? And the current instantly will go to zero. We know that this particular resistive element, it doesn't have storage. It can only dissipate. And the response, I of the system, will instantly go to zero. Let's have a look onto an example of dynamic system. Now, for the similar circuitry, let's make it an arrangement of RL configuration. Here again, we expect some current. Let's some value of R, some value of L, some voltage V1 apparently. Right. Now here we can say this particular voltage. Now, if I use Kirchhoff law over here, what I can get is V1. This must be equal to I times R plus L di over dt. This is what I'll expect in the first case apparently. And the moment I short this voltage source, the value of current will never go down to zero instantaneously. And the current which I'll be getting over here, it would be what would have been the actual current times e to the power minus t over tau. That's what it's going to look like. And for an RL circuit, the time constant tau is L over R. Based on the selection of the values of inductance and the resistance, the current is going to decay. In the case of a resistor, we observed the moment the voltage was made zero, the current would fall down instantly to zero. However, for an inductor and RL based system, we'll expect the curve to look like this. And that is technically, this is the segment where when we say memory is getting used. This particular LR or RL setup is utilizing its stored energy. And that's where we use the logic of memory. So a static system is the one wherein the output depends only on the present input, and these are considered as memoryless systems. Whereas the exact opposite is a dynamic system, which is considered with the presence of memory. And as I said, memory, the output depends not only on the present input, but also on the past inputs which has been applied to the system. Like in the case of this particular inductor, we can see over here, it is displaying a very good example of delivery of stored energy. And that's what we call as a dynamic system. Let's move on to the next difference. The time variant and time invariant system based on the variance of time. Now, say for example, if we consider a basic R network, or for that matter, in the room wherever you are sitting and watching this video, consider the fan present over there. And let's assume the time at this moment is 10 o'clock in the morning. If you turn the switch on, the fan is going to rotate, it's going to reduce the ambient temperature, it's going to circulate the air. Will you expect the same process? Will you expect the same response from the fan when you do the same switching of the fan tomorrow, or maybe next week, or maybe next year? Yes, you will. The response of the fan based system, it doesn't change with time. It doesn't matter whether you are doing it at the end of the day, or at the beginning of the day, or in the middle of the day, any time for that matter. The response of such a system, a time invariant system, is independent of the time at which the excitation is applied. Whereas a time variant system, the response, it depends on the time at which the signal is applied or the excitation is applied. I can give you an example for that. Now, for a time variant system, for a time invariant system, I have given you, I told you, like a basic input output system, maybe a fan, a light, that works well. A heater based system, an air conditioner based system, that's all right. For a time variant system, we can consider a scale, maybe a flight based mechanism, wherein, say, by Newton's second law, we can say force depends on mass and acceleration, right? Let's assume I'm expecting response in terms of acceleration for a particular flight based system, say, right? Now, here we know the mass of the flight based system, it depends on the actual empty mass of the flight and the mass of the fuel which is present in the flight, which is never going to be the same as the flight takes off. Now, for this, we can say the mass over here is a completely changing quantity. There will be a variation in mass as the flight begins its journey. Now, the acceleration which you will be expecting in the beginning with F equal to ma. So let's say A is equal to F by m1 is the initial mass, and let's say acceleration 2, I'd say A is equal to F by m2. This is the final mass, or maybe during the motion of the flight. And this particular mass would have reduced down because of falling of fuel, or because of burning of fuel. And these two components, which I considered as the response, are never going to be the same. Now, this is an example of a time variant system. So, in a time invariant system, irrespective of the time when you apply the excitation, the response remains same based on the magnitude of the excitation that we must consider here. However, for a time variant system, the response of the system changes with respect to time because there are some inherent changes in the internal system. With this, let's move forward. Causal and non-causal systems. A causal system is non-anticipatory, and its output, it's only dependent on the input which is already received, maybe at the present input or maybe the past input. However, it will never consider, or it will never try to anticipate what exactly could be the input in future. Whereas a non-causal system, it tries to anticipate. A simple example would be a causal system is in and around us. It's totally around us. Whereas for a non-causal system, if you observe, now say for instance, we have a cricket match tomorrow, suppose. Now based on the condition of the pitch, we'll select our bowlers. We'll choose which batsman should we get down first and which one should come later. Now that is anticipation. We are trying to anticipate the future response of the system. Based on that, we are changing our excitation. Now, to give you an example, uh, we can consider a missile tracking system. Suppose there is a war, and the enemy country has thrown some sort of missile towards your own country, and you are, as the control engineer, working for safety. Now, that particular missile, you would observe, would be a continually moving system. And the moment when you launched a defense mechanism, at that particular instant, the target would be some location XYZ in space. And as time continues, the missile is moving, so should your target when the defense mechanism is launched. And it should go and hit. Now, this is an example of a non-causal system, wherein the system basically has to anticipate the future, and that is done based on the past. And output of these kind of system, it depends on future inputs as well. Now, to give another example, the weather forecast system that we have, suppose you have to go out maybe this weekend. You'd be observing, you'd be Googling it around and checking what would be the weather condition at your nearby location. And that is basically an anticipatory system which works on the past input. It observes the particular time of the year, maybe in last 5 years, and it obtains a fit based on which it can tell you or suggest you what could be the expected weather this weekend. Now, this is all for the causal and non-causal systems. Now, with this basic understanding, we can come down to a brief understanding of control system. Now, control system, it can be called as a set of devices or units or abstract ideas or biological processes which directs the input to other system and it regulates its output. Now, a control system, it alters the response of a plant. Now, here, the word plant or the word system is similar. It can be used interchangeably. There is not a problem. In this series, I'll be using the word system. However, if any chemical engineer is watching this particular video, they can consider the system as a plant. Right. Let's have a look onto this. So, controller, which I'm about to define here, is basically it is a set of devices or it's a unit which directs or controls the input to the system or plant so that the output is controlled and it is as per the expectation of the user. You as a control engineer or we as a control engineer, we have the complete rights on selection of the input or the reference and output or the excitation. Based on that, we have to design the system, and we can expect, if we have designed a very good controller over here, we can expect the output to meet our expectations. There is a term called disturbance in control systems. Now, these are the undesirable signals which would affect the response of the system. Suppose if we consider an air conditioner based ventilation system in a closed room, as we discussed earlier, the input is an excitation in form of electrical energy and the output is change in temperature. Now, say for instance, we begin with a room which has, say, two people inside. two of you, your friends maybe, inside. And there is a sudden change in the number of people. Now, for the initial case, just with two people inside the room, the AC would have given a particular temperature, would have brought down the ambient temperature to what you have desired that you set up through the remote. However, if the number of people in the room change suddenly, now this air conditioner has got a different temperature to deal with. This will be referred as disturbance, and it is basically disturbing the response. For this case, the response, as we said, is the temperature of the room. Now, to depict a disturbance signal in a control system, you would be showing that the system gets a disturbance, and this is going to affect the output. Now, while designing the controller, there would be some set of or some margin of uh, selection or choice that you would make, which would eliminate the disturbance signal. This we'll discuss later on. Now, open loop control systems. In an open loop control system, the control action from the controller, it is independent of the response of the system. Now, say for example, the same good old fan we can consider, no issue. Irrespective of the temperature of the surrounding or the ambience, if you turn the switch on, if you place the regulator, say at number 2, that particular speed will be constant, and the circulation of air would be constant, and the temperature which has fallen down would still be constant. However, the ambient temperature might vary. Now, depending on that, suppose you need to automate the system. Now, for example, let's begin with a normal system wherein you turn the switch on and you're in the room and it's quite sunny day supposedly. If you turn the switch on, the fan would be rotating, but you yourself have to observe whether it circulating the air to the fullest, wherein are you comfortable. If you're not, you'll have to either raise the regulator or reduce the regulator. But now, this is an example of an open loop control system wherein the control action from the controller is independent of the response of the system. It's totally independent. And these systems, it do not monitor the response, how it is moving through. It doesn't worry about the response. It doesn't have a mechanism of observing the response. There is a controller, give the excitation, it gives the control signal, it goes as an input to the system, and the system responds to it as an output. Now, if there is any disturbance, we can consider the same case. If there is an increase in number of people and the fan mechanism is working, if the number of people changes from 2 to 10, then the input which you provided will not be sufficient. You'll have to increase the regulator from 2 to 5, or say the highest number over there, so that the temperature comes down to normal, or the air is circulated in a good fashion. It could be an example of open loop system. These are not autonomous systems. These are a system whose control action would be independent of the response of the system. Next is closed loop control system, which is exactly different from that of an open loop system. Here, the output, as you would see, the output will be observed continuously by the controller. Now you can see, based with the help of the sensor mechanism, the output is being sensed and it is compared with the input or the excitation with the reference, and an error signal is being generated here, would be generated here, and this would be fed to the controller, and the controller action signal or the control signal would now consider the output. Now, say for instance, if you have given a 10 units of reference here, and the response here due to some disturbance, say it is 15, or say it is lesser than that, maybe 7. You expected 10, but you got 7 here. The sensor, assuming the gain to be 1, which we'll understand later, however, assuming the gain to be 1, the value 7 from the response will be fed back over here, and there would be a comparison and there would be a difference of 3 units. And based on this particular magnitude of error, the controller will change its action signal and will give input to the system, and based on that, the output will be regulated. This will be done till we achieve what we actually wanted as the reference. Now, this system, as you observe, the output is being fed back to the input. We call these as feedback control systems. Now, there are two types of feedback control systems again, a negative feedback, a positive feedback, which we'll see later on. Let's consider one very good example which we come across in our daily life, driving mechanism. Now, here, suppose the car is a system which you are supposed to control. So, assume that you are driving. And now, let's say that I need some reference speed on my vehicle through, if I'm on for a meeting. If I'm going through, I need some reference speed. Say, for example, I need 60 kilometers per hour. Then I have that in my mind and I press the accelerator such that the speed that I observe in the sensor, this is the sensor mechanism, I'm sorry for the word sensor, the speedometer and your eyes, they combinedly act like a sensor there. Supposedly, you press the accelerator pedal to some angle and you obtain some speed here. Now, say for example, I needed a reference of 60 kilometers per hour, and I press the pedal and I obtain here 50 kilometers per hour. Now, that will be observed by my eyes on the speedometer. And based on that, since the speed is lesser, let's look at this abstract idea of feedback path. This is what we were talking about earlier. There's an abstract idea wherein the sensor or the eye and the speedometer based mechanism, it gives you the actual speed of the system, of the car, and your brain compares that with the reference what actually you want. And that particular difference is converted in terms of angles for the pedal to be pressed. And this control signal will be moving forward to the accelerator pedal, and that will drive the engine. So this particular system here is basically an actuator and the engine based system, wherein the output from the brain, which actually would say, no, the speed is low, you're supposed to increase it, press the pedal more. Now, that particular angle of depression in the pedal will be given to the actuator, and this actuator will control the dynamics of the engine, and based on that, the output is going to increase or decrease as per the choice, depending on what you have observed from the speedometer. Let's have a look onto this. The disturbance signal, what do you think would be a disturbance in a car-based mechanism? The bumps on the road, the speed breakers, a ramp, wherein you are expecting a speed of 60, but the slope of the ramp is letting the car fall down in speed. And then you observe it again in the speedometer. Your brain senses it and it thinks, no, there is a difference. The speed is lesser. So you press the pedal more and you get the system moving. And this process continues till you have attained the speed of 60 kilometers per hour, your reference for that matter. Now, that's a very good example of a closed loop control system, which is a negative feedback system over here. We'll learn about negative and positive feedback in later sessions. Now, for this particular example that we saw just now, the plant here or the system here is the car, the controller is our brain, the actuator The actuator is basically a switch which controls the input to the system or to the plant. In the fan-based mechanism, I can say that the switch is the actuator. Now, for this particular example, pedals of the car, the accelerator pedal of the car is an actuator because it is driving the engine. It is driving or injecting more fuel into to the engine, and based on that, the speed is varying. Now, the reference here is the desired speed. The control signal is the angle by which the pedal is getting pressed or released. Maybe you may need to release it if the speed is higher than what you have expected. The response is the actual speed of the car, the disturbance is speed breaker, and the feedback, it is the observed speed by the driver, by you, by me, on the speedometer. Now, the combination of the speedometer and the eye is referred as a sensor here. Now, with this, we'll be summarizing today's lecture. We saw a very brief overview of control systems and its need in engineering, a very little of that. We'll elaborate that in further sessions. We saw the classification of control systems. We saw a couple of examples of control systems and the significance of a feedback mechanism. This we can revisit now. Now, the car-based mechanism that we just saw was a closed-loop mechanism, closed-loop negative feedback mechanism there. Now, say for instance, due to some reasons, suppose I'm a guy wearing a spectacle, yeah? Due to some reasons, I remove the spectacles and I'm unable to see the speedometer. Not quite visible to me, supposedly. In such a case, if there are disturbances on the road in terms of speed breakers or bumps on the road, now there is a ramp, supposedly. Now my brain knows that I need a speed of 60 kilometers per hour. But my sensor system is faulty because I have removed my spectacles. Let's take it as an example to an open loop system wherein the eye cannot see the speedometer. Now there is nothing which the brain can compare the reference with. And the actuation which you did, which I placed on the pedal, would be at the same angle. And this might lead to an accident. So let's wear my spectacle and get the sensor ready. Now, once the sensor is ready, I can observe it. I can observe the speedometer. I can sense the speed which actually I'm moving with the vehicle. My brain can compare that with the reference what actually I want. And based on that, I can change the pedal or the depression or the release of the acceleration pedal. There's a small concept of noise in systems, which I can tell you as an introduction, maybe. If you remember the closed loop system that we just discussed now, the disturbance acts directly on the system in terms of the speed breaker, as I said, for a car vehicle driving mechanism, as I said so. There is a term called as noise. This is generally observed in the feedback path. Now, say for example, I told you that the sensor in a car-based mechanism is your eye, my eye, and the meter. I observe it. It sends a signal to my brain that compares with the reference, gives an error signal. Based on that, gives an actuation signal. Based on that, the depression or the release of the accelerator pedal is done, and the car attains speed, whatever I desired, whatever my brain needed, technically the controller here. Imagine if the speedometer is foggy, or if my spectacles are foggy. If this is the case, then the response from the sensor here, I can observe Suppose I draw the speedometer. I'm sorry for the drawing here. However, suppose if I draw the speedometer, and if the sight is foggy, my eyes would not be able to judge where exactly the pointer is present on the scale. Now, for that case, what my eyes would see would be a variation in speed. I do not know what exactly it is. It may be between 50 and 60, and I would consider that to be, say, 55. That depends on the judgment of the driver, my judgment at the moment. And this particular input or feedback will be given to the brain to compare with the reference. However, if the noise were removed, there is a good chance the pointer would have shown to 59. There is another chance that the pointer would have shown 51 here. This will lead to a change in judgment that may lead my brain to think the speed is lesser or the speed is higher. And based on that, the actuation signal or the control or the angle of depression of the pedal might change, and the actual response of system might vary. So a feedback system is really important in order to attain what exactly the control engineer or the designer or the user expects from the system. With this, we call an end to the session. Thank you for being with us, and stay tuned for the later part of this particular series. Thank you.